Good morning, students. I am Suneetha, Assistant Professor of Chemistry from Kakatiya Government College, Hanamkonda. Today we are going to discuss about aromatic hydrocarbons. There, our subtopic is electrophilic substitution reactions. So, first of all, what are electrophilic substitution reactions? Let's see. These are the substitution reactions which are initiated by electrophiles. The substitution reactions which are initiated by electrophiles are called electrophilic substitution reactions. And we are going to study about electrophilic substitution reactions shown by benzene. We have already discussed benzene is an aromatic compound which is unsaturated compound, but it does not undergo addition reactions readily, whereas it undergoes electrophilic substitution reactions readily due to its stability or aromaticity. Now, what are the different types of electrophilic substitution reactions shown by benzene? Let us see. There, first one is nitration. Second one is sulfonation. Next reaction is halogenation. Next one is very important, Friedel-Crafts alkylation. And last one is Friedel-Crafts acylation. These are the 5 very important electrophilic substitution reactions shown by benzene. Now let's discuss about each and every electrophilic substitution reaction along with its reaction mechanism. Okay. Now first of all, let's discuss about nitration. Nitration. So nitration reaction of benzene. Benzene, when it is heated with concentrated nitric acid, it will give nitrobenzene. Benzene on heating with concentrated nitric acid, it will give nitrobenzene. So, generally nitration mixture, it increases the rate of the reaction. Instead of simply concentrated hot nitric acid, we can also use nitration mixture, but increases the rate of the nitration reaction. Now, what is nitration mixture? Nitration mixture is nothing but the mixture of concentrated nitric acid and concentrated sulfuric acid. So, the mixture of concentrated nitric acid and concentrated sulfuric acid is called nitration mixture, and this mixture can be used for the nitration of benzene for the better yield and high rate of reaction. Here in this nitration reaction, an electrophile NO2 plus, this is called nitronium ion, is used. So this electrophile NO2 plus is released from the reagent, that is nitric acid. And here in this reaction, sulfuric acid, it acts as a catalyst. So sulfuric acid acts as a catalyst, and NO2 plus, that is the nitronium ion, which is used as an electrophile in this nitration reaction, is released from the reagent, that is concentrated nitric acid. Okay, now let us see the reaction. Here, this is benzene. When it is treated with nitric acid, that is HNO3. Okay, so we wanted to show the electrophilic substitution of this NO2. I wrote this HNO3 like this. Okay, this is nothing but nitric acid, and here sulfuric acid is taken as a catalyst, and the mixture is heated to 50 to 55 degrees centigrade, or less than 60 degrees centigrade. Let me say less than 60 degrees centigrade. To that, this mixture is heated. Then we will get a nitro group, which is introduced on one of the carbon atoms, replacing one hydrogen atom. So that's why this is called electrophilic substitution reaction, because the electrophile NO2 plus is substituting one of hydrogen atoms on benzene. Thus, we get nitrobenzene as a product. Okay, the other products obtained here are H3O plus, and the sulfuric acid is regenerated here. Okay, now let's see the reaction mechanism of this nitration reaction. Mechanism of nitration. This involves three steps. The first step is generation of an electrophile NO2 plus. The first step, electrophile is generated by the action of sulfuric acid, that is the catalyst, on this reagent. Okay, so this reagent is nitric acid. This nitric acid, it abstracts, due to the presence of lone pair of electrons on oxygen, it abstracts one proton from sulfuric acid. One proton from sulfuric acid. Then what happens? We will get protonated nitric acid. And this protonated nitric acid, it breaks here. It breaks here, okay, to form H2O and NO2 plus. So this is heterolytic cleavage takes place here. Then as this oxygen is bearing positive charge, heterolytic cleavage of this bond ON bond takes place to form H2O and NO2 plus. So NO2 plus is an electrophile which is generated in the first step. So in the first step, nitric acid reacts with sulfuric acid to form the electrophile NO2 plus. Okay. Now let us see the second step. The second step, this NO2 plus, it goes and attacks NO2 plus. It goes and attacks one of the carbon atoms containing a pi bond. One of the carbon atoms with a pi bond. Then with the help of this pi bond, this NO2, it forms a bond with one of the carbon atoms here. Then what happens? Then what happens? The carbon which is next to this carbon where electrophile is attacking, it gets the positive charge. And this positive charge is delocalized, or it participates in resonance with the two other pi bonds present in the benzene ring. So due to this type of delocalization, what happens? More number of resonance structures arise, and as the number of resonance structures increases, the stability of this particular species also increases. So like this, we get 1, 2, 3 resonance structures. Okay, and these structures are known as sigma complex. Sigma complex. Then in this sigma complex, a new sigma bond is formed in between one of the carbon atoms and this NO2 group. Okay, then in the next step, what happens? The sigma complex, in the third step, sigma complex loses a proton. Okay, this H plus is lost, and this bond pair, it goes inside. Thus, this positive charge disappears, and the aromaticity is again regained by the benzene ring. Okay, so this H plus is lost to HSO4 minus, which is present in the reaction mixture, and this is a fast step where we get a nitrobenzene and the catalyst H2SO4 is regenerated. This is the third step. So in the first step, I'll show you the first step. HNO3 concentrated nitric acid reacts with concentrated sulfuric acid to form the electrophile NO2 plus, that is nitronium ion is generated. So step 1 is generation of electrophile. In the second step, this electrophile, it goes and attacks one of the carbon atoms with a pi bond to form a sigma complex. This is the second step. And third step, the sigma complex, it loses one proton to the other part of the reagent or catalyst to form the desired product, that is nitrobenzene is produced. Okay, this is a first step where this one is a fast step, and in the previous one, that is second step, this is the slow step, that is rate determining step, this one slow step. Okay, now this is about the three steps involved in the nitration. Now let's discuss about the next chemical property of benzene, that is another electrophilic substitution reaction of benzene, that is nothing but sulfonation. This is sulfonation. So what is sulfonation? Sulfonation is the process in which a sulfonic acid group is introduced into the benzene ring. Sulfonic acid group is nothing but SO3H group. SO3H group. This is introduced into the benzene ring. Okay. So this happens with concentrated sulfuric acid. With concentrated sulfuric acid, benzene gives benzene sulfonic acid. So benzene It gives benzene sulfonic acid with the hot and concentrated sulfuric acid. Hot and concentrated sulfuric acid. And in this reaction, sulfur trioxide SO3, it acts as an electrophile. And we know that electrophiles, either they may be positively charged or there may be electron deficient molecules. Here SO3 is an electron deficient molecule. Okay, it acts as an electrophile in this sulfonation reaction. Okay, in the sulfonation reaction, SO3 acts as an electrophile. Right. So let's consider the example here. So benzene, it reacts with concentrated sulfuric acid to form benzene sulfonic acid. On benzene ring, one hydrogen atom is replaced by sulfonic acid group. Here SO3 acts, acts as an electrophile and it replaces one of the hydrogen atoms of this benzene ring to form benzene sulfonic acid. Okay, so thus it is an electrophilic substitution reaction. And this one, the reaction may not be stopped here, and in presence of the hot concentrated sulfuric acid are the sulfuric acid along with SO3, that is known as oleum H2S2O7. This is H2SO4 plus SO3. A mixture of sulfuric acid and SO3 is known as H2S2O7, that is oleum. If we use this as a reagent, then what happens? The reaction does not stop here and we will get this compound, that is benzene sulfonic acid. It is benzene metadisulfonic acid, that is, and 1 and 3 position sulfonic acid group is present. Therefore it is benzene metadisulfonic acid is produced when we use oleum as a reagent. Oleum as a reagent. This is about the sulfonation of benzene. Now let's see the reaction mechanism of sulfonation. Reaction mechanism of sulfonation. So in the mechanism, the first step, what happens? The electrophile sulfur trioxide SO3 is generated. Okay, so in this, what happens? Sulfuric acid, it uh, gives it undergoes ionization to form H3O plus, HSO4 minus and SO3. This is a slow reaction. This is reversible reaction and slow reaction. We can easily see. So this is hydronium ion H3O plus, and the other ion produced here is HSO4 minus bisulfate ion, which is called, and here the electrophile SO3 is generated. So step 1 is generation of electrophile. So in this 2 moles of sulfuric acid, it undergoes ionization to release SO3 as an electrophile. Okay. Now let us see the second step. The second step, this SO3, which is electron deficient molecule. Here we can see the orbital, which is vacant orbital. It has a capacity to gain, okay, accept a pair of electrons. Thus it is an electron deficient molecule, therefore it is an electrophile. So as this is an electrophile, here an extra electron pair is present in the form of a pi bond. So with the help of this, it forms a bond with one of the carbon atoms of this. Then what happens? A bond is formed in between SO3 and this one of the carbon atoms of benzene at the position of pi bond. Therefore, then what happens? With the help of this, it forms a bond with this S. Therefore, here this adjacent carbon, it suffers with a positive charge. Right. So there is a positive charge on the adjacent carbon atom. And this positive charge is in delocalization or in resonance with the remaining 2 pi bonds present in the benzene ring. Therefore, it will be having such type of resonance structures. So these structures are known as sigma complex. Sigma complex. Okay, so this is a carbonium ion. You can see on carbon positive charge is present. So these are the carbonium ions, and which is called sigma complex, and the sigma complex is stabilized by resonance as this positive charge is in resonance with the remaining 2 pi bonds in the benzene ring. Okay, so thus a substituted benzene CSO3 is substituted, and that is it forms a bond with one of the carbon atoms. Thus, we will get a sigma complex. In the next step, what happens? This sigma complex, it loses this H plus, then a substituted compound will be formed. So, then this is step 2, attack of electrophile on benzene ring. Okay, to form a sigma complex. This part we can understand. And here we can easily see this SO3 is a neutral molecule. Once it is forming a bond with this yes, it gets a negative charge. Okay, SO3. One of the oxygens present here. One of the oxygen atoms in SO3, it gets a negative charge. Okay, now this is sigma complex in this on SO3 negative charge is present. Now in the next step, what happens? The sigma complex, it loses this proton which is bonded to the carbon to which this electrophile is bonded. This proton is lost. Therefore, this bond pair of electrons, they go inside and the aromaticity is regained by this ring. Okay, you can see here aromatic ring. Okay, this is a first step. Thus we will get this compound where this oxygen atom of this SO3 group is bearing a negative charge. Now it abstracts a proton from this H3O plus which is present in the reaction mixture. In the first step, it is generated along with the SO3, that is electrophile. So this compound now it abstracts a proton from H3O plus, whereby here we get SO3H. See, you can see SO3H, and other product is H2O. So this is third step in the step 3, a third step in the mechanism of sulfonation. Okay, so this is the second electrophilic substitution reaction of benzene we discussed. And now let us see the next one, that is another electrophilic substitution reaction of benzene, that is halogenation. This is halogenation, right? Now, what is halogenation? This is nothing but uh, substitution of one of the hydrogen atoms of benzene with any one of the halogens like chlorine or bromine generally. Okay, chlorine or bromine are used. So benzene gives halobenzene when heated with halogens like chlorine or bromine in cold and dark in presence of a Lewis acid like FeCl3. So Lewis acid like FeCl3 is used as a catalyst. And in this the reagent is chlorine or bromine, any halogen, and benzene. This benzene, it is the substrate. It reacts with chlorine in presence of FeCl3 to form chlorobenzene. If it is if we say halogen in general, then halobenzene. Okay, so X we should write, X2 we should write here. So here chlorination reaction we have given, where benzene, it reacts with chlorine in presence of Lewis acid, that is a catalyst, FeCl3 to form chlorobenzene. Okay, now this uh, dichlorination is also possible. So this, it again reacts with 1 more mole of chlorine to form 1,2-dichlorobenzene, and this is ortho-dichlorobenzene or ortho product, and 1,4 positions if chlorine atom is present, then it is known as para-dichlorobenzene. This is ortho-dichloro and para-dichloro. So this mixture is obtained when this chlorobenzene is subjected to chlorination. So initially, we get chlorobenzene, which again undergoes chlorination to form a mixture of ortho and para dichlorobenzenes. So this is about halogenation reaction. So benzene in presence of Lewis acid like FeCl3 in dark, in the cold condition, it combines with chlorine to form chlorobenzene. Now let's see the mechanism of this halogenation reaction. Mechanism of halogenation reaction. In this first step is generation of an electrophile. Step 1. generation of an electrophile. So chlorine, it reacts with FeCl3. This FeCl3, it is Lewis acid, we said. That is, it has the capacity to accept a pair of electrons. Okay, so from this Cl dash Cl, that is chlorine molecule, it abstracts a Cl minus, it forms a bond with FeCl3 to form FeCl4 minus, FeCl4 minus, and Cl plus ion is generated. This is only the electrophile we need. Okay, in the chlorination of benzene. So in the chlorination of benzene, the electrophile generated is chloronium ion. Ium ion means the one which is having positive charge. Hydronium, chloronium, bromonium, okay, ammonium. So Em means positive, we should remember. Okay, so this is Cl plus, that is chloronium ion produced in this reaction. So how it is obtained? This chlorine Cl2 molecule, uh, it gives 1 Cl minus, that is a heterolytic cleavage of the bond takes place, and we will get a Cl plus ion, and Cl minus, it forms a bond with FeCl3 to form FeCl4 minus. So this is the step 1. In this step 1 chloronium ion, the electrophile is produced, which is required for the chlorination of benzene. Now in the second step, let us see. Step 2, we know. In the step 2, what happens? The electrophile, it forms a bond with the one of the carbon atoms of benzene using one of the pi bonds. Benzene, it has 3 pi bonds. With the help of one of the pi bonds, it forms a bond with this electrophile. Okay, now let's say this is our point of interest. Each carbon has one hydrogen, but here only we are showing the electrophilic attack. Therefore, here hydrogen we have shown, because the loss of this hydrogen we should show. Okay, otherwise each carbon has hydrogen, no doubt in it. Okay, right now this with the help of this pi bond, it forms a bond with this chlorine. You can see a new sigma bond is formed in between carbon and chlorine. So as this pi bond, it forms a bond with this chloronium ion. Then what happens? The adjacent carbon, it gets the positive charge. Okay. Now the positive charge, now it is in resonance with the remaining 2 pi bonds. Thus we get 2 other resonance structures, and the all these resonance structures, they give stability to this particular ion. This is a non-aromatic carbonium ion, which is called a sigma complex. And in the step 2, a sigma complex is produced when this electrophile chloronium ion, it forms a bond with one of the carbon atoms of benzene ring. Okay, now step 3, let us see. And the third step, what happens? The sigma complex, it loses a proton. It loses a proton of this carbon. Okay, then what happens? We get our required product, that is chlorobenzene, the final product. This is a first step, and this proton is given abstracted, let me say, by this FeCl4 minus. Then FeCl3, our catalyst is regenerated. The other product produced is H and Cl, that is HCl. HCl is the product produced. So in the halogenation reaction, or chlorination is the specific example we consider. In this chlorination reaction, benzene, it reacts with chlorine in presence of a Lewis acid catalyst, that is FeCl3, to form chlorobenzene, and other product produced is HCl in this reaction. Okay, anyhow, this is the catalyst which is regenerated. Right? So this is chlorination. Similarly, we can also show the bromination reaction of benzene. Instead of Cl2, we should write Br2, then we will get bromobenzene. Okay, FeBr3 we should consider as a Lewis acid catalyst. Okay, next let's discuss about another chemical property, very important chemical property of benzene. This is also an electrophilic substitution reaction. That is nothing but Friedel-Crafts alkylation. Friedel-Crafts alkylation. Okay. So in this Friedel-Crafts alkylation, um, we introduce an alkyl group into the benzene ring in presence of a catalyst is known as Friedel-Crafts alkylation. Okay, so alkyl group is introduced. Alkyl group is introduced into the benzene ring in presence of a catalyst like AlX3. Okay, AlX3, AlCl3, AlBr3 like that. Okay, aluminium chloride, aluminium bromide. So this is only called Friedel-Crafts alkylation. So in Friedel-Crafts alkylation, benzene, it reacts with an alkyl halide. It reacts with an alkyl halide, that is RX, alkyl and halide RX, in presence of a Lewis acid like anhydrous AlX3 to produce alkyl benzene. So alkyl benzene is the product produced in the Friedel-Crafts reaction due to alkylation. So this alkylation, it takes place in presence of AlX3, a Lewis acid as a catalyst, and the reagent is alkyl halide, that is Rx. Okay, so benzene plus Rx in presence of AlX3. This is delta, that is meant for heating. We will get alkyl benzene, and the other product produced, one H is replaced by this R group, therefore that H and this X, that is the negative part of the reagent or nucleophilic part of the reagent is X minus, and here from this H plus. So H plus and X minus in the form of HX is produced as another product of this reaction. So, and this is only known as Friedel-Crafts alkylation reaction. So in Friedel-Crafts alkylation reaction, benzene combines with alkyl halide in presence of AlX3, a Lewis acid, to form alkyl benzene. Alkyl benzene. Now let's see its reaction mechanism. So mechanism of Friedel-Crafts alkylation. Okay, here step 1, first step. In all these electrophilic substitution reactions, step 1 is generation of an electrophile. So here in this reaction, the electrophile used is this one, alkyl carbonium ion R plus is the electrophile generated. Now let's see how it is obtained. So alkyl halide, it donates this X minus to this AlX3, which is a Lewis acid, which has a vacant orbital which can accept a pair of electrons. So this X minus, it forms a bond with AlX3 to form AlX4 minus. You can see AlX4 minus. Okay. So initially what happens? See, this is the transition state where a bond is present in between R and X and AlX3. So slowly what happens as the reaction proceeds, the bond between this R and X breaks and a bond between this Al and X is formed. So here a new bond is generated, here the old bond is broken. Okay, then what do we get? AlX3 minus this one, AlX4 X3 plus X minus, altogether AlX4 minus, and the required electrophile, that is R plus, that is alkyl carbonic cation or alkyl carbonium ion is generated. So this is the electrophile we require in the Friedel-Crafts alkylation reaction. Now this is the step 1 where alkyl carbocation or alkyl carbonium ion is generated as an electrophile. Now let's see the second step. In the second step, what happens? This alkyl carbonium ion, it forms a bond with one of the carbon atoms with the help of a pi bond, the help of a pi bond. Then what happens? A sigma complex is produced, which is stabilized by resonance due to the presence of two other pi bonds in conjugation with it. Okay, thus the sigma complex is stabilized, and this in the next step, what happens? It loses a proton to the other part of the reagent. Okay, it loses this proton from the sp3 carbon to this reagent to form alkyl benzene, that is alkyl substituted benzene, and this H and X, HX is produced, and this is AlX3 what we have taken as an catalyst that is regenerated. So this is the Friedel-Crafts alkylation reaction. Now let's see one specific example for Friedel-Crafts alkylation. Okay, example for Friedel-Crafts alkylation. So this benzene, it reacts with alkyl halide. This is 1, 2, 3. So 3 carbon alkyl group, that is nothing but propyl. Propyl chloride. N propyl chloride. N stands for normal, no branching. Okay. So this is N propyl chloride. Benzene is treated with N-propyl chloride in presence of AlCl3, that is Lewis acid, as a catalyst. Then what happens? This alkyl group, it gets attached to one of the carbon atoms. See, here N-propyl benzene is produced as a product. N-propyl benzene is produced as a product. Okay, so the other product may be H from this carbon of benzene and this Cl in the form of HCl. Okay, is obtained. This is one simple example for Friedel-Crafts alkylation. We can also consider ethyl chloride or methyl chloride here instead of this much very big alkyl group. CH3Cl is simply you can take. Then we will get CH3 and group is substituted on benzene, that is nothing but toluene. So methyl benzene is called toluene. So if we consider methyl chloride here instead of propyl chloride, we will get methyl benzene, that is called toluene. That is the simplest example we can give. Okay, for alkylation. Next, in this alkylation, what is this? If we consider primary alkyl halides, so primary alkyl halides, this is a primary alkyl halide. Okay, if we consider primary alkyl halides in this alkylation reaction, they give carbocations in the first step, that is the electrophile generated. So they will undergo this carbocations, they will undergo rearrangement to produce isomeric reagents, that is they get rearranged to give some other carbocation. So if the different carbocation goes and attacks the benzene ring, then we will get more number of products. That is because of this reason the polyalkylation takes place. Polyalkylation takes place. So here let us consider the example. Benzene treated with propyl chloride, N-propyl chloride in presence of AlCl3. This is the expected product, that is N-propyl benzene. But along with this N-propyl benzene, we also get this. Okay, this is isopropyl benzene. So how do we get this? Because in the reaction mechanism we have considered in the first step, carbonium ion or alkyl carbocation is produced here. This is the reagent, this is the catalyst. The Cl minus goes with AlCl3 in the form of AlCl4 minus, and this CH3 CH2 CH2 plus, that is N propyl carbocation is produced. This undergoes rearrangement to form rearrangement. During the rearrangement, what happens? This H plus goes to this carbon. Okay, then this carbon suffers with a positive one hydrogen atom. From this it goes to this carbon, and this carbon it gets the positive charge, you can see here, due to rearrangement. Then what happens? This is primary carbocation, this is secondary carbocation. If this primary carbocation goes and attacks this benzene ring, we will get this product. If it goes and attacks benzene ring, we will get this product. Okay, this one. If it goes and attacks benzene ring, this is the product obtained. If this goes and attacks benzene ring, this is the product obtained. So thus, if we consider primary alkyl halides in this alkylation reaction, there is every possibility of getting more number of products because of polyalkylation, and this polyalkylation arises due to the rearrangement of carbocations. Okay, so this is about the limitation, we can say, of Friedel-Crafts alkylation reaction. Now let us consider the next property of benzene. That is one more important property, that is Friedel-Crafts acylation. Friedel-Crafts acylation reaction. In this Friedel-Crafts acylation reaction, uh, an acyl group is introduced. Introduction of acyl group. Acyl group is RC double bond. One more bond should be there to this carbon. Okay. Introduction of acyl group into benzene ring in presence of a catalyst is called Friedel-Crafts acylation. And here acyl halide, it gives acyl carbocation which acts as an electrophile. In this reaction, acylation reaction, acyl halide is considered as a reagent which produces acyl carbocation or acyl carbonium as an electrophile, and that goes and attacks benzene ring to form the final product as acyl benzene. Acyl benzene. Okay. Now let's see the example here for acylation reaction. Benzene. This is acetyl chloride, CH3COCl. This is acetyl group. This is chloride, acetyl chloride. Benzene reacts with acetyl chloride in presence of AlCl3, which is Lewis acid, as a catalyst, and benzene is the solvent here. At about 80 degrees centigrade. At about 80 degrees centigrade, the reaction takes place. Then the product obtained is this COCH3 group, that is acetyl group, goes and attacks one of the carbon atoms to give acetyl benzene, which is also known as, this particular molecule also known as acetophenone. Acetophenone. One means C double bond O. You can see here. C double bond O, ketone. It's a ketone. Acetophenone is a ketone. So this is phenyl group and this is methyl group. So it is methyl phenyl ketone. Okay. So this is the common name of this particular compound is acetophenone. So acetophenone is obtained when benzene is treated with acetyl chloride in presence of a Lewis acid like AlCl3. Okay. Now this reaction, the same product, we can also get instead of acetyl chloride if we use acetic anhydride. This is acetic anhydride. Acetic anhydride is the compound obtained from the dehydration of acetic acid. So two molecules of acetic acid, if they lose one molecule of water, we get acetic anhydride. That's it is known as acetic anhydride. N means no, hydride means water. So from acetic acid, water is removed. Okay. So this acetic anhydride can also be used as a reagent in the Friedel-Crafts acylation reaction. So instead of acetyl chloride, if we use acetic anhydride, then also this acetyl group gets introduced onto the benzene ring to form acetophenone as the product. And this reaction also takes place in presence of AlCl3, that is anhydrous AlCl3 as a catalyst. Okay. Now let's discuss the reaction mechanism of this particular reaction. Friedel-Crafts acylation reaction mechanism. The step one is generation of an electrophile. Generation of an electrophile. So here as RCOCl, general reagent we considered, that is acyl chloride. It is known as, okay. AlCl3 is the catalyst, which is Lewis acid, has a vacant orbital. Now it has extra electron pairs, therefore it forms a bond with this. Then what happens? This with the help of this extra electron pair, it forms a bond with AlCl3. You can see here. Then this bond breaks as Cl is bearing positive charge. It is more electronegative than carbon. Therefore, if this bond breaks, heterolytic bond fission takes place. The bond pair, it goes with the Cl in the form of AlCl4 minus, and this carbon now gets positive charge or CO plus. Or CO plus. Okay. So this is acyl carbocation. Acyl carbocation. Okay. Acyl carbocation is generated in this reaction. Step 1. Now in the second step, you can see Second step, what happens? This acyl carbocation, which is an electrophile, it forms a bond with benzene, one of the carbon atoms, with the help of one of the pi bonds. So this is electron excessive compound, that is a nucleophile, and this is an electrophile. A bond is formed in between this carbon and this carbon. Okay. Then what happens? This is hydrogen present on this particular carbon, and a new sigma bond is formed in between this carbon and um, carbocation carbon of this acyl carbocation. Okay, now the adjacent carbon, it gets positive charge, and this positive charge in resonance with the two other pi bonds, that is alternate pi bonds are present. Therefore, due to delocalization or resonance, it gets three resonance structures, and this is known as sigma complex, which is non-aromatic, which is a carbocation, and the sigma complex, in the next step, it loses a proton, it loses this proton, okay, to form a ketone, a final product. Ketone is obtained. This is phenyl, this is alkyl. Alkyl phenyl ketone is produced, and this H plus, it goes with this AlCl4 minus in the form of H. It combines with this and to form HCl and AlCl3. AlCl3 is the catalyst which is regenerated, and other product obtained is HCl. So in acylation reaction, benzene combines with acyl chloride to form acyl benzene and HCl. Okay, acyl benzene and HCl. Now, what are the limitations of this el- electrophilic substitution reactions? That is especially Friedel-Crafts alkylation reactions. Let's see. First one is rearrangement of intermediate carbocation. Then what happens? Polyalkylation takes place. Second one is presence of strong withdrawing groups like NO2 group, and this is trialkyl amino group. Next one is carboxylic acid group. Next, this one acyl group. Next, trifluoromethyl group, and another one is SO3H group. So such type of electron withdrawing groups, when they are present on the benzene ring, then what happens? They lowers the product yield. So electron withdrawing group present on the benzene ring. Electron withdrawing groups examples we have given here: SO3H or COOH, that is carboxylic acid group, or acyl group, or CO group, CF3 group, etc. groups, NO2 group, etc. Then what happens? They deactivate the ring. Thus, the product yield will be less. Okay, so this is one another limitation. And next one is we can see here as vinyl halide and aryl halide. They do not easily give carbocations and cannot be used. Only alkyl halides can be used in this alkylation reaction, Friedel-Crafts alkylation. And instead of alkyl halide, if we use aryl halide or vinyl halide, they generally do not produce carbocations easily. Because of that reason, they cannot be used in this reaction. This is one more limitation. Now, other limitations, if we consider here, presence of electron releasing groups like alkyl groups, that is R groups, okay, will lead to polyalkylation due to rearrangement. Okay. Here we have given this example. This is benzene. Okay. When treated with isopropanol in presence of a Lewis acid like BF3 on heating to 60 degrees centigrade, then what happened? We get isopropyl benzene, and other product is here uh, 1 4 1 and 4. Okay, 1 4, that is para. 1,4-isopropyl benzene. 1,4-diisopropyl benzene is obtained here. Okay, dialkylation is taking place. So like this, presence of electron releasing groups. Electron releasing groups lead to polyalkylation. So as this group is present on this, the benzene ring gets activated and it undergoes another alkylation and one more alkylation to form polyalkylated product. This is one example here we have given. Next one is after introduction of one alkyl group, that is alkyl group is ring activating group. We will discuss about this. The ring gets activated and further substitution takes place to form dialkyl derivative. So here polyalkylation is taking place in this reaction. So these are all the limitations of Friedel-Crafts alkylation reactions. Now let us see a few questions which are related to the topic which we have covered today. Okay, so that the first one is describe Friedel-Crafts alkylation with suitable example. This is the very important question. And next one is what is Friedel-Crafts acylation? Give an example. Acylation, Friedel-Crafts reactions, both are very important. Next, explain electrophilic substitution of benzene to nitrobenzene. So nitration of benzene we should write here. Next one is discuss halogenation reaction of benzene with an example, either chlorination of bromination of benzene we should write. Okay, so electrophilic substitution reaction, statement, equation followed by mechanism we should write. Next, what are the reagents used in bromination, nitration and sulfonation of benzene? So reagent used, bromination, bromine Br2, nitration, HNO3 and sulfonation, concentrated sulfuric acid. Okay, so these are the reagents used in this reaction. So these are the few questions which are related to the topic which we have covered today. Okay, now thank you all. We will discuss the rest of the topic in the coming sessions. Thank you once again.